Now, you may or may not have had a physics course, so you may or may not, even if you've had physics, you may or may not understand where this pendulum force comes from. So let's just sketch vertical line and a pendulum at a position away from vertical. Now, the string exerts a force along its length. The string can only pull. The string can't push, and a string can't exert a force. A string in this direction can't exert a force in this direction or this direction. It can only pull. If you stretch it slightly, it pulls back. So this is our force, which I'll call tension. I could use just a single letter T for tension, but I'm going to write out the whole word. And tension is a vector. It's a force, therefore a vector. Now, if we look at that tension vector over here all by itself, it's easy to see that this tension vector has a component in the horizontal direction and a component in the vertical direction. So this would be tension in the y direction, and this would be tension in the x direction. Now, the tension in the y direction simply counters the downward force of gravity, and it's the downward force of gravity that causes the tension to be there in the first place. If the displacement of the pendulum from the equilibrium position is small, then there's not much difference between the tension, the magnitude of the tension in the string, and how much tension there is in the y direction. And in that case, without going through all the details, it turns out that our x tension is the net force on this pendulum mass and that tension is equal to some constant times x, where x is the position of the pendulum with respect to equilibrium. This means that if you pull twice as far back, you get twice as much net force, twice as much tension in the x direction, and also that the force of tension is back toward the equilibrium. And we can see that that's the case, that the x component of this force, and I'm not going to draw all the projection lines, but that this x component of the force is indeed back toward the equilibrium, so that our net force is negative kx. Now, by Newton's second law, the net force is the mass times the acceleration. So we have mass times acceleration equals negative kx. Now, acceleration is the derivative of velocity. Again, recalling that x is a function of t. Once this thing is set in motion, x becomes a function of t, the acceleration is a function of t, and the velocity is a function of t. Now, the velocity v prime, well, that's nothing but x prime prime, because the velocity is just the derivative of the position. We conclude that the acceleration is the second derivative of the position, and this equation then becomes mx double prime equals negative kx. This is consistent with what we saw in the preceding video, and again, our task is going to be to solve this equation for the function x. I guess I should also note that this becomes x double prime equals negative k over m times x. and this is the form in which we saw the equation previously, although it's very clear that these two are completely equivalent. And that double prime doesn't really look much like a double prime, kind of blurred together. Anyhow, you get the idea, and this is the reason that the position function satisfies this relationship.